First of all, let's look at some of the things that happen when you mix different types of acids and bases together. If you mix a strong acid together with a strong base, this is what will happen. The strong acid will have a spectator, like hydrochloric acid, for example, would have Cl minus, or hydriodic acid would have I minus. That's not involved in the reaction. The same thing is true for the strong base. That's going to have a cation that's a spectator, like sodium hydroxide would have sodium, for example. The net ionic reaction for a strong acid, strong base reaction is always just going to be the formation of water from the H plus from the strong acid and the OH minus from the strong base. This is a one-way reaction, and K is essentially infinity for this type of a reaction. So strong acid, weak base reactions are going to go to completion, and we can assume that there will be no H plus and no OH minus to any appreciable extent left after the mixture occurs. In this example, we're asked what are the major species in a mixture of 500 milliliters of 0.1 molar HCl and 500 milliliters of 0.2 molar NaOH. So what will happen when the HCl is in solution is it's just HCl completely dissociating to give you H plus ions and chloride ions. And the NaOH is going to completely ionize, and that's going to give you Na plus ions and OH minus ions. So in the end, what's really going on here is you have just some HCl producing H pluses, NaOH just produces OH minus, and your net ionic reaction is just going to be H plus plus OH minus, and that's producing, without reversing, that's producing water. So what are the major species? Well, we're not going to see very much H plus, and we're not going to have very much OH minus. We are going to have a lot of chloride ion because that spectator is going to be around. It's not doing anything. It doesn't influence pH. We also are going to have a lot of sodium ions. And then we're going to have water. But OH minus and H plus are not going to be present to any great extent at equilibrium here. Or it's not really at equilibrium. It's a one-way reaction. Another possible mixture that you might have is a strong acid, weak base mixture. In a strong acid, weak base mixture like this, B is your base. This is generic base. It's reacting with water, like weak bases do. It's producing to an equilibrium a conjugate acid. We're calling it Hb plus, and then hydroxide ion. The K for this reaction is Kb, which is going to be a small number because it's a weak base. Here's the strong acid. When it's in solution, it's going to be H plus reacting with OH minus to make water. Where does the OH minus come from? Well, in this mixture, the weak base is producing some OH minus. And so that means, if you think about this from a Le Chatelier's principle standpoint, because this second reaction has a K of essentially infinity, every time, or every mole, we could say, of the OH minus that gets produced by the weak base is going to immediately be consumed by reacting with H plus from the strong acid. And that means we're going to keep shifting the reaction to the right. So we can think, another way of thinking about this is we can add these two reactions together. If you think about that, just summing up all the products that we have in all the reactants, we can take away water from each side. We can take away OH minus from both sides. And that's about all that we can take away. Now, what is K for this reaction? Remember, the law of multiple equilibria, or the rule of multiple equilibria, says that if you add two reactions together, the K for the sum of those reactions is the product of the two Ks for the reactions that you added together. So K in this case is Kb times infinity. Well, anything times infinity is just infinity. So basically, this becomes a one-way reaction where the reactants are the H plus from the strong acid, the weak base, and the products are the conjugate acid of that weak base. So this is what it looks like if you put that all together. It's a one-way reaction the H plus from the strong acid is just adding to the weak base, neutralizing the weak base, and making its conjugate acid. So strong acid weak base reactions go to completion as well. This question is asking, what are the major species in the mixture of 250 milliliters of 0.01 molar NH3 and 125 milliliters of 0.01 molar HCl? So this, you might be tempted to say, well, the major species are just going to be water and chloride ion from the HCl, and then the conjugate base of ammonia. But we have a little bit more difficult problem here because of the fact that we have the same molarity, but we have 250 milliliters of our base and only 125 milliliters of our HCl. So if we think about what's going to happen here, the H plus from the HCl is going to react with the NH3, and that's going to produce pretty much a one-way reaction, NH4 plus. Now we're starting out with twice as much NH3 as we have H plus. So when this reaction goes to completion, we're still going to have some NH3 left over. And that's just a limiting reactant thing. I mean, if you think about 125 times 0.01, that's 12.5 millimoles of HCl. We could actually do a before change after chart here. This is 1.25 millimoles. And this is 2.50 millimoles. And then there's none of this, of course. And then so the change is going to be the H plus is the limiting reactant. We're going to lose 1.25 millimoles of both of these, and then we're going to gain 1.25 millimoles of NH4. So in the end, we don't have any H plus. We're going to have 1.25 millimoles of NH3, and we will have some NH4 plus. Now, you probably didn't have to go through all of that whole Rice chart or BCA chart to come up with this answer, but what are the major species? There's still some NH3 left. We have produced some NH4, that's present. There's going to be chloride ion from the H plus, and then obviously there's water because that's going to be the background that all of this is happening in. Another possibility that you could have is a strong base weak acid mixture. In this case, we would have a generic weak acid, let's call it HA, that would dissociate in water, ionized, to give you H pluses and A minus. K for that reaction or that equilibrium would be Ka. And here's your strong base. Strong base is going to be OH minus from like sodium hydroxide or something like that, reacting with H pluses that are provided by the weak acid to produce water. And K for that is essentially infinity. So because every H plus mole that gets produced in the ionization of the weak acid is going to immediately be consumed by reacting with the hydroxide from the strong base, Le Chatelier's principle would suggest that there's a shift in that top reaction to the right, making this essentially a one-way reaction. So if we think about summing these together, this is what we would get, just adding everything up. And the equilibrium constant, or the equilibrium constant is essentially infinity. And then if we look at what we can cancel out of here, H plus drops out, and our net ionic reaction is just going to have hydroxide ion reacting with the weak base to produce water, and with the weak acid to produce water and the conjugate base. So that's what we would end up with. So this leads us to the conclusion that a strong base weak acid reaction also goes to completion. So all of the reactions that we've seen so far go to completion. Strong acid, strong base goes to completion. Strong base, weak acid, strong acid, weak base. They all become one-way reactions. This question is asking us, what are the major species in a mixture of 250 milliliters of 0.1 molar HNO2, that's a weak acid, and 125 milliliters of 0.1 molar NaOH. So here what the reaction is going to be is the OH minus from the NaOH is going to react with the HNO2, that's the weak acid, and this proton is going to be donated to the OH minus, strong acceptor of protons, and that's going to make water. And then we're going to get NO2, 1 minus, which is the conjugate base of HNO2. This is a one-way reaction. Now we do have that limiting reactant thing here. We have twice as much HNO2 as we have OH minus. And so when this reaction goes to completion, we're still going to have some HNO2 left in solution just because of the limiting reactant thing. But there won't be any OH minus. There will be a bunch of NO2. In fact, however many moles of this we have left, we'll have that many moles of NO2. Water will be a major species, and then we will also have sodium ion. That's the spectator from the sodium hydroxide. Those would be the major species. Now let's take a look at a weak base, weak acid mixture. So here's our weak acid. K is Ka. Generic weak acid is Ha ionizing to H plus and A minus. Here's our generic weak base, B. It's reacting with water and reaching a dynamic equilibrium with its conjugate acid, Hb plus, and hydroxide ion. K for that reaction is going to be Kb. Now, if we add these reactions together, this is what we get, and the K is going to be the product of Ka times Kb. Let's look at what we can cancel out here. We know that OH minus and H plus don't exist to any appreciable extent together because it's a strong acid and a strong base. So these are going to actually react to form water. So they're not there. And that allows us to cancel off this water. So when we put this all together, we're going to have the weak base plus the weak acid making the conjugate base of the weak acid and the conjugate acid of the weak base. And the K for this reaction is Ka times Kb. But since both of these are weak, it's a weak acid and a weak base, when we multiply two small numbers together, we're going to get a really, really small number. So K is much less than 1, and we can say that a weak base, weak acid reaction is not going to reach completion. Here's an example. What are the major species in a mixture of 250 milliliters of 0.1 molar HF, that's a weak acid, and 250 milliliters of 0.1 molar NH3? Here we have equal volumes of equal concentration of both acid and base, so that simplifies things a bit. According to this pattern that we have up here, we're going to have NH3, that's our weak base, reacting with HF, that's our weak acid, and that is going to produce A minus, that's the conjugate base, in this case F minus, and then the conjugate acid of NH3, which in this case NH4 plus. And this is a reversible reaction because remember K is going to be pretty small. So this is actually, that shouldn't be written that way. This should really be double arrow because this is a reversible reaction. So what are the major species? Well, we're going to have some of this. We're going to have a bunch of this. We're not going to have very much this. We're not going to have very much of this because K is very small. We will have a lot of water. Now we need to spend a little time talking about the acid-base properties of salts. And there's a couple of rules that we're going to go through, and then we're going to learn a lot of this by mostly examples. If the cation is the cation from a strong base, so in other words, you have strong bases like NaOH, let's say, or CaOH2, something like that. That cation and that cation we're talking about here, if that's the case, then it doesn't affect the pH of the system. And we're going to look at why it doesn't affect the pH of the system in a little bit. Here's an example, sodium hydroxide. Essentially is a one-way reaction. It's going to completely ionize or dissolve to Na plus and OH minus. So for this to go backwards, because K is essentially infinity, to take OH minuses and get them back together with Na pluses and take that OH minus out of solution to affect pH is virtually impossible, because if you flip this reaction around, that means you have to take the reciprocal of K. So that's 1 over infinity, which is essentially 0. So that means this reaction is not going to go forward to any extent at all. So that has no effect on pH of the system. Cations from strong bases don't affect the pH of the system. If the cation is the conjugate acid of a weak base, which happens occasionally, then it does affect the pH, and it tends to lower the pH of the system because it's an acid. Here's an example of that. If in the salt ammonium chloride, the cation is ammonium ion. Ammonium ion is a conjugate acid of ammonia. And so it's going to ionize to produce ammonia and then H plus. And because it's producing this H plus, that means it is going to lower the pH of the system. So look at your cations, and they're going to be in two categories. They're either something like ammonia, and there aren't very many of these, and that means that they're going to be acids, or they're going to be the cations of strong bases, and then they're going to have no effect on pH. If the anion is the anion of a strong acid, it does not affect the pH of the system. So we have the 6 strong acids. We're looking at those 6 anions. If those are the anions in the salt, it does not affect the pH of the system. Here's why: because we'll use hydrochloric acid as an example. Hydrochloric acid ionizes completely. K is essentially infinity. So if we were going to try to get this to go backwards, to have the chloride ions react with the H plus to go back to HCl molecules, the K for that reaction would be about 0. So that is not going to happen. So chloride, iodide, sulfate ion, those things will not have any effect on pH. Any anion, that's the anion from a strong acid. You just got to remember what your 6 strong acids are. So now we're looking at the effect that anions could have on a solution. If the anion is the conjugate base of a weak acid, well, because it's a base, that will tend to raise the pH of the system. So for example, let's take a look at this. Sodium acetate, because it's a group 1 salt, will completely split up into sodium ions, which have no effect on pH. We know that because they are the cation from a strong base, sodium hydroxide. But here we have this acetate ion. This is the conjugate base of acetic acid. So what that's going to do is react with water as a weak base and produce acetic acid and hydroxide. And the fact that it is producing these hydroxide ions in solution means that it is going to have an effect on pH. OH minus concentration is going to go up and pH will rise. So let's look at some examples. Will the following solutions be acidic, basic, or neutral? Let's take a look at this one. If we have calcium nitrate, it's going to split up and it's going to give you these ions. Calcium 2 plus ion, and it's going to give you nitrates. Stoichiometrically, it's 2 nitrite ions. This is going to not contribute to pH because it is the cation of a strong base, calcium hydroxide. No effect. This, however, is the conjugate base of HNO2. So because it's a base, that is going to make this a basic solution when you dissolve this salt in water. So what will happen there? This NO2 that's in solution is going to react with water. It's going to produce some HNO2, and it's also going to produce hydroxide, and that's what influences pH. Another example, NaCl. What's NaCl going to do? It's going to split up and it's going to give you Na plus ions and Cl minus ions. This is going to be a completely neutral solution. We know this because this is the cation from a strong base, sodium hydroxide. This is the anion from a strong acid, hydrochloric acid. So this is going to be a neutral solution when you dissolve this one. Another example, ammonium bromide. This is going to split up and give you, NH4 plus ammonium and bromide. The bromide is going to have no effect on pH because it is the anion from a strong acid, hydrogen bromide or hydrobromic acid. But this, remember this cation, that's an acidic cation. It's the conjugate acid of ammonia. So what it's going to do is it's going to take water molecules NH4 pluses, and donate protons to them. And that's going to give you H3O pluses and NH3, the conjugate base. And so that means it's going to drop the pH. This is an acidic salt. I'm sorry, I'm switching notations because I'm usually not using the hydronium notation, but I did that time. And here we have potassium bicarbonate. That's going to split up and give you K plus ions and HCO3 minus ions. The potassium is the cation from a strong base. No contribution to pH. But this is an anion that starts with H. And that's something that you want to look for. Anions that start with H are acidic anions. What's this going to do? HCO3 is going to, it's going to dissociate, and it's going to give you H plus ions and carbonate ions. So because it's producing these H pluses in solution, that means this is going to be an acidic salt. Okay, let's look at one more. And this is a complicated one because if we look at what happens when this salt dissociates, you're going to get ammonium, NH4 plus, which is an acidic cation. So that would tend to make the mixture acidic. But we're also going to get NO2 minus, which we saw earlier is a conjugate base of a weak acid. And so that's going to tend to make the solution basic. So when you have a conflict like this, we have to look at which one is stronger, the acid or the base. And we'll do that by comparing the values of Kb and Ka. For ammonia, Kb is 1.8 times 10 to the minus 5. So that means for ammonium, NH4 plus, the Ka is going to be equal to Kw divided by the Kb for ammonia. So that's 10 to the negative 14, that's Kw, divided by approximately 10 to the minus 5. So this is going to be about 10 to the negative 9. And for NO2, 1 minus, the Kb, well, that's going to be about Kw, so that's 10 to the minus 14th, divided by Ka, which is 10 to the negative 4 approximately. So that's approximately 10 to the minus 10. So in this case, Ka is bigger than Kb, and so that comparison tells us that this is going to be an acidic salt when the substance dissolves. Okay, now to our final topic, and that is buffers. Here's the idea behind a buffer. When a mixture contains an acid and its conjugate base both, that mixture resists changes in pH. So for example, if a mixture contains both HF, which is an acid, and F minus, which is its conjugate base, this equilibrium exists. Now, how does this resist changes in pH? Think about what happens to this system, thinking about Le Chatelier's principle. How will this system respond if H plus is added to the system? Well, if I add H plus to the system, the reaction is going to shift to the left, according to Le Chatelier's principle, because Q is going to get too big, and so you're going to lose products and make reactants. So that mitigates the effect of adding that extra H plus. Instead of the pH dropping, the H plus is going to turn into HF, and that successfully reduces the change in pH because HF is a weak acid and H plus is a strong acid. So we took a strong acid and shifted this reaction backwards to turn it into a weak acid, and that has less of an effect on pH. Also, we can think about how will this system respond if OH minus is added to the system. If OH minus is added to the system, it will immediately react with the H plus that's produced in this equilibrium. That reduces the concentration of H plus and causes the reaction to shift to the right to make more H plus. So instead of our OH minus driving the pH up dramatically, the presence of that H plus can neutralize it and then we shift to the right, and instead of having the strong OH minus, that's a strong base, we just produce a weak base, F minus, which will have much less of an effect on pH. So let's look at some examples. What is the pH of a buffer that's made from 0.1 molar HNO2, and a Ka is given there, mixed with 0.1 molar NaNO2? So let's think about what's going to actually happen when these two are mixed. We're going to set up this equilibrium. First of all, the NaNO2, that's going to completely ionize, and it's going to give us Na plus ions and NO2 minus ions. That's what's going to happen. So that means we're going to have this ion present, and we're also going to have this acid present. Well, this is the conjugate base of that acid. So now we have just created a mixture that has an acid and its conjugate base, and that's a buffer. Okay, so what is the pH going to be? Let's set up an ice chart to kind of analyze this. So we have HNO2. It's going to be in equilibrium with H+, it's ionizing, and its conjugate base, NO2-. So initially, we have a common ion effect going on here. We have 0.10 molar HNO2, and we also have 0.10 molar NO2-. And before this reaction reaches equilibrium, there's no H+. What's our change? Stoichiometry is 1:1. We're getting pretty used to seeing these things now. And at equilibrium, this is going to be 0.10 minus X. This will be X, and this will be 0.10 plus X. So Ka here, being concentration of H plus times concentration of NO2 minus, divided by the concentration of HNO2. Well, that's going to be 4 times 10 to the negative fourth equals X times 0.10 plus X divided by 0.10 minus X. And we're going to see this happen over and over again. These are always weak acids, which means that exponent is always going to be small, or almost always going to be small. So that X in the differences, top and bottom, that's actually a plus X, that's ignorable. So this is going to be, to a very good approximation, this will just be X, because 0.1 divided by 0.1 is just 1. So that means that the hydrogen ion concentration here, which is what X means in our chart, is actually just equal to the Ka value. So what's the pH? Well, the pH is negative base 10 logarithm of that then, 4.0 times 10 to the negative fourth, which is 3.40. Okay, here's another problem. What is the pH change if 10 milliliters of 0.1 molar HCl is added to 1,000 milliliters of water? Okay, so what happens if we put HCl in water is it fully ionizes to H plus and Cl minus. So every mole of HCl we put in the water produces a mole of H plus, and that is going to influence pH. How much? Well, let's figure it out. Let's say we take our 10 milliliters and we multiply by our molarity, which is 0.10 moles of H plus in every 1,000 milliliters. And that gives us 0.0010 moles of H plus. So what's the concentration of H plus here? Well, we have 0.0010 moles of H plus in how much volume? Well, we had 1,000 milliliters. We added 10 more, so that's 1,010 milliliters, or 1.01 liters. So this works out to 9.9 times 10 to the negative 4. So what's our pH? The pH is equal to negative base 10 logarithm of that, 9.9 times 10 to the negative 4. And that comes out to 3. So the question wasn't what the pH is, it was what was the pH change. So if it was added to water, pure water is going to be just pH equals 7. So we experienced a pH change of 4 pH points, which is significant. That's 4 orders of magnitude, or in other words, the solution got 10,000 times more acidic by adding this HCl. Okay, so now we're going to see the real value of buffers. In this problem, we're asked, what is the pH change if 10 milliliters of 0.1 molar HCl, so that's the same amount of the same acid, what if that is added to 100 milliliters of the buffer instead of being added to water? So let's set some things up here. One thing we know is this buffer, we just calculated in the previous problems that 3.40 is the buffer pH. So we want to know how much does the pH of this buffer change in this instance. Let's think about what's in the solution and what's going to change. So what's going to change is we have H plus, and that's going to react with the conjugate base in the buffer and produce more of the conjugate acid that's in the buffer. So that's a one-way reaction because it's a strong acid, weak base, and so that's what's going to occur. Let's set up a BCA chart and find out what we're left with once this reaction is done. So what do we have before? Well, if we think about the H plus constant, or the number of moles of H plus, we have 10 milliliters of H plus, and it's 0.10 moles of H plus present in every 1,000 milliliters. So that means we have 0.0010 moles of H plus. So that we can put in here, 0.0010. How many moles of NO2 do we have? Well, in that solution, we had 100 milliliters of 0.10 molar NO2 minus. So that would be per 1,000 milliliters. And so this gives me 0.010 moles of NO2 minus. And we had the same volume and same concentration of the HNO2. So both of these start out as 0.010 moles. And then we have a change. H plus, there's much less of it, so that's the limiting reactant. We're going to lose all of that. We're going to lose the same number of moles because of 1-to-1 stoichiometry of NO2 1 minus, and we're going to gain that many moles of HNO2. So that after this change takes place, H plus is down to nothing. Now it's not going to stay at nothing. We're just trying to get ourselves to where we can set up an equilibrium concentration. We're going to take 0.010 and we're going to lose 0.001, which leaves us with 0.009 moles of NO2. And we're going to take 0.01 and add 0.001, which is going to leave us with 0.011 moles of HNO2. So when we have this reaction over with, the concentration of NO2 minus is going to be 0.009 moles in our new volume. So we added 100 milliliters and 10 milliliters together. That's 110 milliliters, or in liters, that's 0.110 liters. So this concentration ends up being 0.082 molar. And the concentration of HNO2, the acid in the mixture, well, that is going to be 0.011 moles divided by 0.110 liters, and that's just 0.1 molar. So now we can set up a Rice chart. So the HNO2 in this buffer is going to be in equilibrium with H plus ions and its conjugate base, the NO2 minus. Initially, the concentration of HNO2 is 0.10. We're going to assume there's no H plus until the equilibrium is reached, and this concentration is 0.082. Change, well, the stoichiometry is 1 to 1, so we lose X moles of HNO2, gain X moles of each H plus and NO2 1 minus. At equilibrium, then, this is 0.10 minus X, this is X, and this is 0.082 plus X. So the Ks, or the Ka for this buffer, you'll recall, is 4 times 10 to the minus 4. Maybe you won't recall, but I did. 4 times 10 to the minus 4, that's the Ka for HNO2. That's going to be equal to X, because that's the H plus concentration, times 0.082 plus X divided by 0.10 minus X. Because 10 to the minus 4 is small, I'm going to ignore these two unless my answer shows that I couldn't have. So now I solve for X by just multiplying both sides by 0.1 and then dividing both sides by 0.082, and I come up with X is equal to 4.9 times 10 to the negative 4. So what's the pH? Well, the pH is minus the base 10 log of that number, because that X represents H plus concentration. And when we work that out, that comes out to 3.31. That's the pH. So what was the pH change? We started at 3.4 and we went down to 3.31. So that is only a change of 0.09 pH points. In contrast with just the pure water, that changed by 4 entire pH points. So much smaller response by adding that HCl to the buffer. We can create a buffer by just taking a strong acid and reacting it with a weak base. And here's how that works. If we have a weak base and we put it in the presence of a strong acid, this reaction that we've already seen is going to make some of the conjugate acid of that weak base. So now we have just created a system that has a base and its conjugate acid, or an acid and its conjugate base, and that is therefore a buffer. So here's a question related to that. What's the pH of a buffer created when 0.0050 moles of HCl is added to 100 milliliters of 0.10 molar ammonia, which is a weak base, and the Kb is given? What's going to happen here? Well, NH3 is going to react with the H plus, and it's going to produce NH4 plus. That's what the response is going to be. So let's figure out what we started with. We have, for NH3 moles, we have 100 milliliters, and the concentration is 0.10 moles of NH3 per 1,000 milliliters, which leaves us with 0.010 moles of NH3. So that's what we're starting out with, 0.010. That's the before. We don't have any of this yet before the change takes place. How much H plus do we have? It says we added 0.0050 moles. So 0.0050 moles. H plus is limiting reactant. We're going to use that all up. 0.0050 get burned up. Also, because of 1-to-1 stoichiometry, we lose 0.0050 moles of NH3, and we're going to gain 0.0050 moles of NH4 plus. So afterwards, we have left 0.005 moles of NH3, don't have any H plus, and we're going to have 0.005 moles of NH4 plus. So that is what's present in our system. Now let's figure out how does that work out to a pH. So now let's make a rice chart. Let's say that this NH3 reacting with water is going to be in equilibrium with its conjugate acid, NH4 plus, and hydroxide ion, and finding hydroxide ion is going to allow us to get the pH. So starting concentrations, initial concentrations, this was 0.0050. It's not actually 0.0050, and that's because this is in 100 milliliters of solution. But in the end, we're just going to end up with ratios anyway, so I'm just going to leave it as moles. I would get the same answer if I divided by 0.1. That would be fine. It would work out great, but I would have to do it. So I'm not going to. Water we don't care about. NH4 plus is 0.0050, and OH minus nothing. Then the change is all 1-to-1. So we're losing X moles of products, gaining X moles of, losing X moles of reactants, gaining 1 X moles of product. At equilibrium, this is going to be 0.0050 minus X. Don't care about water. This will be 0.0050 plus X, and this will just be X. So Kb, which is H plus or NH4 plus concentration times OH minus concentration divided by NH3 concentration, will just work out to 0.0050 plus X times X divided by 0.0050 minus X. And Kb is small. Kb, remember, is only 1.8 times 10 to the negative 5. So again, I'm going to take these X's and then just ignore them because they will not change that value very much. So that means X is just equal to 1.8 times 10 to the negative 5. And that is OH minus concentration. So that means the POH is equal to the negative base 10 logarithm of that 1.8 times 10 to the negative 5, which works out to 4.74. And 14 minus 4.74 will be equal to the pH, because remember, pH plus POH adds up to 14 always. So that means our pH is 9.26. So we created a buffer with a pH of 9.26 by just putting a weak base in the presence of a strong acid. Likewise, we could take a strong base and react it with a weak acid, and that would also create a buffer. So here's your weak acid, HA, reacted with a strong base, OH minus, and we get water, and then we get the conjugate base of that weak acid. So now we have a weak acid and its conjugate base. Those are both present in the same mixture. That makes it a buffer. So for example, if we take KOH, a strong base, and mix that with acetic acid, a weak acid, we get a buffer. Now here's a question about that buffer. How does this buffer against added strong base? So if we add strong base, how does this keep the base from making the pH rise? Here's what we did by adding the OH minus to the acetic acid. We caused this strong base, weak acid, one-way reaction, and we made water because the weak acid is going to donate its proton, and we have C2H3O21 minus, which is the conjugate base of acetic acid. So if we add strong base, well, we have a weak acid to react with it. So that's what will happen. If we add strong base, we'll have OH minus, just like this reaction, reacting with C2H3O2, and it's going to produce water and a weak base. So the buffer turns a strong base into a weak base. Next question is, how does this buffer against an added strong acid? Well, we also have a weak base in this buffer system. So if we add a strong acid, that H plus is going to react with C2H3O2 1-, a weak base, and it's going to accept that proton to make C2H3O2, a weak acid. So we took a strong acid and turned it into a weak acid because that weak base is present in the buffer system. Okay, now you're going to learn a little bit of a shortcut here. This is a really valuable tool called the Henderson-Hasselbalch equation. We're going to start out by just considering a generic buffer. It's made from a weak acid, let's call it HA, and of course its conjugate base then would be A minus. And the question here is, what is H plus at equilibrium? We can set up a ice chart for this. This is the equilibrium that would be established. Initially, we don't know what the concentration is. We're just talking in generic terms here. So let's just call it concentration of HA initial, no H plus, and concentration of A minus initial. So this is a buffer, so you have to have both HA and A minus. What's the change? The stoichiometry is 1 to 1. So it's going to look like minus X plus X and plus X. We've seen this before a lot of times. At equilibrium, it was the initial concentration of HA minus X for HA concentration. For H plus concentration, it's X, and that's what we want to find. And for A minus, it's going to be just the initial A minus concentration plus X. So here's what we know. We know that Ka, in terms of this chart, is going to be equal to X times the concentration of A minus, the conjugate base initial, plus X, divided by the concentration of HA, the weak acid, initial, minus X. Now, Ka is always going to be very small because these are weak bases that we're talking, these are weak acids that we're talking about. So that means that we can ignore these X's in the sums here. So that means it's a reasonable approximation almost all the time to say that Ka is equal to X times concentration of A minus divided by concentration of HA. And we're talking about initial concentrations here. But X is equal to the concentration of H plus, and that's what we want to find here. So we'll solve this equation for X, and that means we're solving it for H plus, and this is what we get. Concentration of H plus is equal to, I'm going to multiply both sides by initial concentration of HA, so it's Ka times concentration of HA initial, and then divide both sides by the concentration of the conjugate base, initial concentration of A minus. And that is the Henderson-Hasselbalch equation, which is a valuable kind of a shortcut for figuring out H plus concentration. Now, there's another form of this that's often much more useful, and that is if we ask not as what H plus at concentration at equilibrium, but what is the pH at equilibrium? So let's take a look at that. Remember, this is our H plus concentration expression. So we know that pH is the negative base 10 logarithm of H plus concentration. So maybe a good place to start would be to take the negative base 10 logarithm of both sides. So base 10 log of H plus, that's going to give us pH. That's going to be equal to negative base 10 log of Ka times concentration of HA initial divided by concentration of A minus initial. But when you take the log of a product, that's the same as taking the sum of the logs of the two things that you're multiplying. So we could rewrite this. We could say negative base 10 logarithm of H plus equals negative base 10 log of Ka minus the base 10 log of concentration of HA initial divided by the concentration of A minus initial. But we know that minus base 10 log of H plus is pH, so we'll just put that in there. The negative base 10 log of Ka is a value that we call pKa. Put that in there. And then let's flip A minus and HA upside down and change the sign from negative log to positive log. So positive log, base 10 log, of A minus concentration initial divided by HA concentration initial. This is the logarithm form of the Henderson-Hasselbalch equation, which takes you straight to pH and is sometimes much more useful. Here's another thing that's very useful about both of these forms of the Henderson-Hasselbalch equation. Because both of these are in the same volume in this system, that means instead of concentration of A minus and HA, we could also just use moles because they're both going to be divided by the same volume. So here's a kind of a summary of that. There's the Henderson-Hasselbalch equation in terms of concentration, but we can also think about the Henderson-Hasselbalch equation in terms of just ratios of moles, if that's easier to use, which it often is. So here's a question. What is the pH of a buffer in which the concentration, initial concentration of the conjugate base is the same as the initial concentration of the acid in the mixture? Well, if these are the same, that means here we are taking the log of 1, which is 0. So that means the pH is just equal to pKa. So if you want to make a buffer of a certain pH, you can just go look for a weak acid that has a pKa that's approximately the same as pH, and you're going to be pretty close. And then you can just sort of tune it up by adjusting the ratio of base to acid in your buffer mixture. So here's a specific question. What is the pH of a buffer made by mixing 50 milliliters of 0.1 molar acetic acid and 50 milliliters of 0.2 molar sodium acetate? Okay, so the sodium acetate is a source of the weak base here, the conjugate base. So NaC2H3O2, because it's a group 1 salt, is going to give you Na pluses plus C2H3O2 1 minus, 1-to-1 ratio. So that means we're going to have, we have equal volumes here, so we're just going to use concentrations. That'll be fine. We're going to have 0.200 molar acetate ion, and we're also going to have 0.1 molar acetic acid. So what's our pH? Well, it's going to depend on the pKa. So the pKa for this acid is going to be the negative base 10 logarithm of our Ka, which is 1.8 times 10 to the negative 5. And that works out to 4.74. So our pH of our buffer is going to be equal to that pKa, 4.74, plus the base 10 logarithm of concentration of A minus, well, that's 0.2, divided by initial concentration of acetic acid, and that was 0.1 molar. So we take the log of 2, essentially here, add it to 4.74, and that will give us our overall pH, and that is 5.04. Okay, so here's the Henderson-Hasselbalch equation for us, and it's asking us this question. This is the same buffer that we were talking about before. So what's going to happen here? Well, if we are adding OH minus to this buffer, it's going to respond by the acetic acid, the weak acid, reacting with the OH minus, and it's going to produce water, and it's going to produce the conjugate base, C2H3O2 1 minus. So what will we have left? What do we want to know if we want to find the pH? Is we have to know the pKa. Well, we have that. It's pretty easy to get. We've already done that. It's 4.74 for this acid. And then we want to know either how many moles of A minus are present and how many moles of HA are present, or concentration. I think moles might be easier to work with in this case. So what do we have here for hydroxide? We have 250 milliliters, or 2.50 milliliters and the concentration is 0.10 moles per liter. That gives us 0.25 millimoles of hydroxide. So if we think about a BCA chart here, OH minus and HC2H3O2 producing water and acetate ion. Our before for hydroxide is 0.25 in millimoles. How much acetic acid do we have? Well, we have 50 milliliters at 0.1 moles per liter. So that gives us 5 millimoles of acetic acid. And we have 50 milliliters of 0.2 molar sodium acetate. So that's going to give us 10 millimoles. What's our change? Hydroxide ion is the limiting reactant. So we're going to lose 0.25 millimoles of everything on the left-hand side. And we're going to gain 0.25 millimoles on the right. So that after this is done, no hydroxide. This will be 4.75 millimoles of acid and 10.25 millimoles of base. So what's our pH after this addition? Well, the pH is just equal to 4.74 plus the base 10 logarithm of base moles, which is 10.25, over acid moles, which is 4.75. So the pH changes to 5.07. And remember, the initial pH for this buffer we figured out in the last problem was 5.04. So that was not much of a change at all by adding a pretty substantial amount of a very strong base.